Good afternoon, everybody. Welcome to our lecture on the California drought. This hasn't really been done previously in any of the climate change, water, and society classes, but this year is special to some degree, and I think that it's an important issue that I think people in this class are particularly going to be well trained in order to address, just because it cross-cuts through so many different fields. So I'm going to talk to you for the next hour or so about the climatological rationale behind the formation of the drought, how this drought fits into California's historical record of drought, and how we anticipate future droughts will occur in California and their associated characteristics. So I wanted to start with an interesting fact, and that's since over the years 1980 to 2003, the U.S. as a whole, droughts and the associated heat waves have accounted for 10 of the 58 weather-related disasters that have an estimated cost of more than $1 billion when normalized to 2002 dollars. Now, this has increased since this study was originally released. I don't have the updated numbers, unfortunately, but the key point here is the fact that drought is a costly disaster on both a socioeconomic scale as well as economically. So there are both impacts to human health, livelihoods, crops, and the overall economy with the occurrences of these droughts. So being able to predict and understand the formation of droughts and their effect on society as a whole is going to be very important going forward, especially trying to understand how these drought conditions will change under future projected climate change. So I'm going to do a quick aside into atmospheric dynamics for a moment. This is the one key concept from atmospheric dynamics you will need to know in order to really understand what happened during the drought. This is the concept of geostrophic wind. For large-scale wind patterns, typically on the order of at least 1,000 kilometers, the large-scale wind is governed by what is known as geostrophic balance, which leads to the geostrophic wind. The basic idea here is that your concept of air parcels flowing from high pressure to low pressure does not necessarily hold on the large scale due to the fact that the Earth is rotating. Because we have rotation of the Earth, we have Coriolis force, and in the northern hemisphere, the Coriolis force is responsible for pushing air parcels to the right. What this means is that for an air parcel originally located in a region of relatively high pressure, although it'll initially begin moving from high to low pressure, the Coriolis force will turn it to the right until Coriolis force and pressure gradient forces balance, in which case the air parcel will be following exactly along lines of constant pressure. This means that in order to understand how air parcels are flowing in the atmosphere, we simply need to look at a map of a pressure field, or correspondingly a map of geopotential heights, and look at contours of constant pressure or constant geopotential height. And what we know from that is that air parcels will tend to move along those contours on the large scale. So this geostrophic balance is the primary driver of synoptic scale winds. Now, as you probably know, the 2013 to 2014 California drought was the driest 12-month period in 119 years of precipitation observations in California. Related to my argument about atmospheric dynamics, the proximal cause of these extremely high dry conditions are associated with a persistent high-pressure anomaly, nicknamed the ridiculously resilient ridge, as commonly appeared throughout the news and whatnot. It's a very catchy phrase in order to describe this ridge. It had the effect of deflecting winter storm tracks away from the state by governing that large-scale wind field. You can see it here in the 500 hectopascal height anomalies to the west of California. Here, California is shown via the black bar. This is a function of time, going from farthest in the past at the top in November 2013 to the end of February 2014 at the bottom. And here showing a cross-section of the geopotential height anomaly at 40 degrees north. What we're looking for here is red on the field which is an indicator of a particular flow direction of the large-scale winds. So wherever we see red, this corresponds to the ridiculously resilient ridge that we saw off of California. And what was particularly unusual was its persistence. The fact that you can see remnants of this ridge starting in November 2013 and follow it down, especially through December 2013 and January 2014, where off of the west coast of California, this persistent high pressure anomaly can be seen very readily in this cross section. So there's a strong relationship that exists between this high pressure anomaly and dry conditions in California. It might be more clear from this plot. This is an ensemble mean of February 2014 showing the high pressure anomaly off of the coast. So here we're showing anomalies from the mean pressure field or from the mean geopotential height field, and contours shown here in black. The presence of the anomaly forces up the geopotential height field off of the coast, which means that contours of constant geopotential height are going to be pushed northwards. So what we gain from this then is the knowledge that an air parcel, which originates, for instance, here in the Central Pacific, will follow along these contours as it makes its way eastwards through the diagram. And the important thing worth noting is that this high pressure ridge then causes these air parcels to sharply divert northwards before they're able to reach the coastline. So the overall wind field then, triggered by this pressure field, kind of looks like these block arrows as they follow along the contours of constant geopotential height. The presence of the high pressure ridge then leads to the wind field to be dominated by a southward or northerly wind over the Pacific West Coast. So most of the winds that were then received during when the anomaly was present are coming from the north. Looking at a satellite diagram from the 23rd of January, 2014, you can see the presence of this ridge very clearly. High pressures are typically associated with fairly calm, clear conditions, but moisture, which is being transported eastwards from the tropics, is redirected by the presence of the ridge northwards and into Alaska. So what we experienced then was greater than average precipitation around Alaska and extremely dry conditions in California, since none of that moisture was able to pass through the geopotential anomaly and into our region. The timing of the ridge was particularly disastrous because so much of the moisture in California falls during that December to February season. And as you saw, that was the key time at which the ridge was particularly persistent. So roughly 30 to 50% of California's water supply comes from these so-called atmospheric river events or Pineapple Express events, which look like this in the figure. This is plotting a vertically integrated moisture field. And what we see from these atmospheric river events, which are responsible for such a large amount of precipitation, is what appears to be a river of moisture originating in the tropics that then drops that moisture over the west coast. With the high pressure ridge then present here, none of these atmospheric river events were able to penetrate through to the California coast, and so we lost out on all of the rainfall associated with those events. So that was the primary driver behind the dry conditions that we experienced. And instead, that moisture was redirected to the north. The consequences were extremely dry conditions experienced in 2013 to 2014 relative to mean values. Here we're showing the precipitation anomaly, that is the difference between the precipitation received during that winter season and the average from 1900 to 2000. Along the whole west coast, precipitation values are basically at the edge of the scale. That is, they were extremely low relative to those mean values. as that moisture was not deposited along the west coast. On a statewide scale, 2014 was the lowest precipitation year on record, shown here. Note that this scale doesn't go from 0 to 40 exactly. But even with filtered values, the period between 2013 and 2014 showed a dramatic drop in total precipitation over this period. Looking at January 18th, 2013 and comparing it with January 18th, 2014, you could immediately see the consequences in the satellite imagery. Here, there's clear green, presence of green vegetation occurring in the Central Valley. You see snow over the Sierra Nevadas, suggesting a relatively healthy snowpack, and snow inward towards the Rocky Mountains, which was not present in 2014. In 2014, the Central Valley was left barren, dry, dusty for the most part. The only way that farms were sustained within that region was via pumping of groundwater, basically via the groundwater reservoir, which naturally forms in the Central Valley. And we did not get anything close to a healthy snowpack over the Sierras, which led to further dry conditions over this past summer, because most of the moisture that we require in California for agriculture over the summer is due to runoff from that snowpack. I'm going to show you a couple plots from a recent paper from Swain et al., published coming from the Stanford group and recently published in the Bulletin of the American Meteorological Society. So this looks at some of the other characteristics of the drought. On the left here, we see the number of years over the 1895 to 2013 period, which had lower observed precipitation than 2013. And as you can see, for the majority of California, there were no years that had less precipitation. As you go farther south into Southern California, that region has, in the past, experienced even drier conditions over the winter season. On the right diagram here, we're seeing exceedance of the mean 500 millibar geopotential height field. So that's associated with the pressure anomaly that we had off of the west coast. And what it says is that the mean geopotential was so high on average that, for the most part, over much of the northeastern Pacific, there were no previous years that had a high pressure anomaly at quite the same magnitude that we experienced. As you can see, though, California in particular was particularly hard hit by this drought event and dry conditions, because as you move farther inland, there are more and more examples of past years in which drier conditions existed. And in fact, as you go farther east towards Colorado, it was actually one of the wetter seasons that they experienced farther inland, because their moisture was coming via a different storm track. If we look at January to December cumulative precipitation, 2014 was by far the driest year. Comparing this with the 1976 drought, we see that even 1976 exceeded 2013 pretty substantially. The black dotted line here representing the mean cumulative precipitation received in California, indicating our dry summer conditions where this curve flattens, and moister winter conditions. So in 2013, we were very far below the mean state of all recorded years since 1895. Looking at 12-month running mean precipitation, that is taking the total integrated precipitation over the past 12 months, January 2014 was very clearly the lowest on that plot over the entire record, and even substantially lower than June 1976, which was the previous record holder. So as I mentioned, we had the existence of this high-pressure ridge off of the northeastern Pacific that cause drier conditions by affecting the mean wind field. The presence of a high pressure region is associated with clockwise motion. And this is exactly what we observed in the 2013 mean zonal and meridional wind field. That is, we observed a tendency for more of the wind to be towards offshore near California and more of the wind to be towards onshore near Alaska. And the meridional anomaly suggested a much stronger wind field originating from the north. And to the west of this anomaly, we saw northward tendency in the average wind field. So the main climatological drivers here, or the meteorological drivers, are fairly clear. We had the existence of this persistent anomalous ridge which redirected winds northward, and its persistence was what made it particularly unusual. In combination, that persistence with the typically moist conditions that we experienced during the winter season led to the drought conditions that we then experienced. California in particular is very susceptible to the occurrence of these, the total precipitation received in California is very sensitive to this high pressure anomaly. Plotted here are the Northeast Pacific geopotential height. You can interpret that analogously as Northeast Pacific pressure, along with California precipitation. As you can see, when the precipitation is down, you're typically having a Northeast Pacific geopotential height which is up, that is associated with a high pressure anomaly, and the reverse in the case of higher precipitation, we typically have a low pressure anomaly in the Northeast Pacific. So this strong correlation is something that we can then use in our climate modeling systems to say, okay, how likely is it that another one of these anomalous ridges will appear? Is there going to be a change on the return time of these events or their intensity? Because the existence of this large-scale synoptic feature is then going to be associated with the cumulative California precipitation for that given year. Okay, I want to go aside for a moment and talk about the Palmer Drought Index. So this is how we take basically precipitation amounts and translate it into a measure of how much drought is being experienced within that region. The Palmer Drought Severity Index comes in a number of flavors, including the PDSI and the Palmer Modified Drought Index. All of these are available from NOAA. They have a series of map generation tools which you can go and use to check out the record all the way back to 1900. The PDSI basically measures conditions. It gives an index between which has no lower bound and no upper bound, but generally if the index itself is less than -4, that corresponds to extreme drought conditions, and if it's greater than 4, that corresponds to extremely moist or extremely wet conditions. This is computed as a function of soil moisture via a supply and demand model. Supply is calculated directly from precipitation, and demand is a measure of how much moisture is being drawn out of the soil from a number of processes. This is a bit more difficult to calculate, but it's basically determined empirically from local temperature and precipitation amounts. Here are some recent droughts plotted across the US. 2002 experienced a particularly significant drought over the Rockies and through southern California. 1980 experienced a drought in North Dakota and in that region. And in 1988, there was another significant drought which appeared kind of along the northern side of the continental US. So the purple index here corresponds to extreme drought conditions over the continental United States, and bright green corresponds to extremely moist conditions. Comparing this with the Dust Bowl, perhaps the most severe drought in the whole history of the continental United States, we can see that under these conditions, pretty much most of the continental United States is under extreme drought conditions as computed by the Palmer Modified Drought Index. Here's the California 1976 to 1977 drought. Interestingly, this drought included both drought conditions along the west coast and drought conditions in the northern Midwest states. Southern California wasn't hit quite as hard, but Northern California was in a state of extreme drought during that time, extending far north. Comparing that to the California 2013 to 2014 drought, we see that the entire state of California here is actually undergoing at least severe drought conditions. And most of it is experiencing extreme drought conditions. And this extended pretty much through Nevada and Arizona and New Mexico. This is also taken in July 2014. Earlier plots showed more extreme drought appearing in the Pacific Northwest, but they were fortunate in that in early 2014 they received significantly more precipitation through the spring season, which provided them with some relief from these drought conditions. So the outstanding questions that then come from the 2013 to 2014 drought, now that we've looked at the current state of the drought, is can we look at the past and can we say, is the 2013 to 2014 drought unusual in the history of California? And we can then ask, is the 2013 to 2014 drought a sign of things to come? Because this drought was so hard-hitting, there has been a significant amount of scientific interest in addressing these two questions. Much of the history of drought was already examined previously, but there were 3 separate publications in the supplementary issue of BAMS, all of which tackled the question of future drought in California, and which I will discuss. So if we look over the past century or so and plot the PDSI for California, 1895 to 2014, well, it's pretty clear from this that the 2014 drought is a new low record for the Palmer Drought Index. That is, this 2014 was the year in which most of the state experienced its worst drought conditions. But for the most part, the state's drought is highly variable. That is, we'll occasionally have a few dry years, a few wet years. The early 1900s actually had several wet years in a row. But it's hard to really extract any significant pattern from this. Looking closely, you may be able to see a slight downward tilt, but I'm not convinced that it's within the realm of statistical significance. So in order to understand this drought then in the context of California's history, we need to look back even farther. So fortunately, there was this paper, a very important paper published in 2007 by Cook et al. And they were able to find very strong correlations between the tree ring record over the US and the Palmer Drought Severity Index. That is, typically during dry years, there was less growth associated with trees over the continental United States, which then led to a narrower spacing on the tree ring record. These reconstructions actually revealed that California in the past has experienced mega drought events. That is, ones which make 2013 to 2014 look like a blip on the radar. And so these mega drought events obviously occurred prior to the advent of industrial civilization. And so the presence of these droughts must be associated with the natural variability of the climate system. So it lends even further credence to the claim that California is an extreme weather state. That is, we are very susceptible to strong variations in variability. Plotting the tree ring record back to 800 AD, you could see the amount of area of the West which is considered to be in drought conditions. This is the 100 years that we have recently in the previous plot. with drier conditions being towards the top of the graph and wetter conditions being towards the bottom of the graph. In particular, you'll notice that in the mid-1800s, there was a particularly large blip. In the mid-1500s, there was a small blip. There were some very long duration dry events, and in particular, 1150 and 1253 were associated with extreme drought conditions that lasted over several decades. And these conditions are associated with the red line here, which it basically mimics the 2013 to 2014 drought. So for an extended period of time, natural variability of the climate system led to these decades-long drought conditions. Plotting it in terms of drought periods, that is, regions in which we have drier conditions and wetter conditions relative to a mean value. There were very long extended drought periods which existed between roughly 1850 and 1060 or so. And then 1150 through roughly 1300 was another period of extreme drought over long duration. Relatively recently, over the past 500 to 600 years, we've seen relatively moist conditions actually in California. So this is indicative that the current state of California's water supply is in response to moister conditions. So perhaps before we started pumping excess groundwater, we were actually at a groundwater high. So these are, in particular, the 1150 drought is what's known as one of the medieval mega droughts, basically a 200-year period in which persistent drought conditions were present throughout the West. And if you were to look at the Palmer Drought Severity Index over the continental United States over 1150 to 1159, representative of one of the peaks of the drought period, what you would see is that pretty much everywhere west of Kansas was in a persistent drought state. Note that the negative PDSI values didn't necessarily carry over to the whole continental United States during this period, as the East Coast actually experienced moisture conditions. So, in conclusion then, I would say that the 2013 to 2014 drought isn't particularly unusual if looking back at the whole 1,000-year historical record of drought conditions. It is unusual over the history of civilization in California. Although past civilizations that have existed in California, the end of those civilizations have been strongly correlated with these very strong drought events which have been observed within the record. Now, the concern is that even without anthropogenic climate forcing, that perhaps in 2013 we will begin transitioning into another one of these historical extended drought periods. And whether or not the natural system is able to remain stable along with significant groundwater pumping that we're now performing on the Central Valley is still an outstanding question. Okay, so let's answer another question then. We've looked at the past drought record for California. We've looked at the present drought. Now let's look at the future. What can we say, knowing everything that we do about how climate is anticipated to change over the next century? What can we say about how drought conditions in California will change? So from the Swain et al. Paper, we had the little soundbite, California's driest 12-month period on record occurred during 2013-2014. And although global warming has very likely increased the probability of certain large-scale atmospheric conditions, that is, we do know that global warming increases North Pacific sea surface temperatures, and increases in North Pacific sea surface temperatures are associated with higher pressures in the Northeast Pacific, perhaps then associated with, which have been shown to be correlated with California drought conditions. The implications for extremely low precipitation in California remain uncertain. So basically what Swain et al. Showed is that the probability of extremely high geopotential height in the northeastern Pacific is likely at least a factor of 4.02 times larger under current climate than compared to pre-industrial. And you can see that already. This is something that we can observe directly in the climate record. If we compare the mean geopotentials observed from the 1980 to 2013 period versus the geopotentials which are observed earlier than that time. So here we see sea surface temperatures, which in general are expected to warm under climate change. And here we see changes in the geopotential field. Note that what we're particularly interested in is the increase of this anomaly that appears over the northern Pacific. What this suggests is that there is a greater tendency now for anomalous high pressures over the northeastern Pacific than there was in prior years, closer to the beginning of the 20th century. And the existence of anomalous high pressure conditions in that region are then associated with these high pressure ridges, which can then redirect moisture farther north. But if we look at the actual change in precipitation amounts in California, here using a multi-model ensemble, so climate modeling system, in order to build a probability density function associated with annual precipitation in California, we observe that there's actually very little change in the total precipitation amounts per year, comparing 1980 to 2013 versus the earlier part of the 21st century. Now this seems kind of strange at first because one would assume that the anomalous high pressures that we've been experiencing in the northeastern Pacific would lead to drier conditions. And we're fairly confident that those geopotential heights will continue to be enhanced into the future. So we are observing in general that 2-meter temperatures in California are higher compared to the early part of the 20th century. But we're also observing that total precipitable water, that is the total amount of water vapor in the atmosphere which can be turned into precipitation, is also increasing. And this is purely a thermodynamic argument. Warm air will tend to hold more moisture than cold air. And since the air temperature is increasing, then there is going to be more water vapor in the system. But we are observing that geopotential heights at 250 millibars, so top of the troposphere geopotential heights, are also tending to increase on average in the northeastern Pacific. So what this suggests is that we are going to have more ridging events. There is a greater tendency for the large-scale meteorological conditions that created the ridging event to occur. So this tail produces a much higher probability. But the increases in precipitable water compensate almost exactly with the increase in that ridging event. So the total amount of precipitation received in a given year within California does not actually change significantly. What this does suggest, however, is that there may be bigger swings between wet years and dry years in California. That is, the extremely dry conditions associated with high pressure ridging in the northeast Pacific may become more common in general, although total precipitation does not change. So from this Wong et al. Paper in 2014, they said that the 2013 sea surface temperature anomalies produced a predilection for California drought, whereas the long-term warming trend appears to make no appreciable contribution because of the counteraction between its dynamical and thermodynamical effects. That is, the atmospheric dynamics conditions induced by the anomalous ridging is compensated for by an increase in total precipitation. One other paper from the BAM supplement was the Funk et al. Paper. And their conclusion was that long-term sea surface temperature warming trends did not contribute substantially to the 2012 and 2013 and 2013-2014 California droughts. North Pacific sea surface temperatures were exceptionally warm, however, and coupled models indicated more frequent extreme precipitation. So what that effectively says is that we know that the North Pacific is warming under climate change, but we could not find a correlation that necessarily led to between the drought event and the warming of sea surface temperatures in the northern Pacific. So looking back at the Palmer Modified Drought Index and our current state of affairs, one can observe a slight trend associated with the PMDI, a slight downward trend. It's unclear at this point whether that is a real trend or simply due to the sample size that we have in order to generate this. There are claims throughout the literature that we can expect this PDMI to continue its downward trend as more and more demands are put on the water supply. But it still remains an open question within the science community. This is the current US drought monitor as of October 28, 2014. Much of the state still suffers from exceptional drought conditions, or as Randall Munro puts it, ludicrous drought conditions. But there is a little bit of optimism, hopefully, in looking forward over the next year. We do know that the existence of warmer eastern equatorial Pacific waters is correlated with the existence of, or is associated with El Nino events. And these El Nino events do affect the North American monsoon, which has the potential to bring moisture to Southern California. There is no particularly strong correlation between the El Nino events and precipitation in Northern California, however. The observed warming in these eastern equatorial Pacific waters suggest an impending El Nino event over the coming winter season. And it is well known that these El Nino events have so-called teleconnections with warm, dry, cold and moist conditions over the whole globe. And in particular for us in California, in this region, typically the El Nino event is associated with slightly higher rainfall in Southern California. From the 3-month climate outlook produced from NOAA, it suggests that at least for January, February, March 2015, we're going to see above average rainfall conditions throughout Southern California, but in Northern California, there's a roughly equal probability of above average and below average conditions. That is, it's expected to be roughly an average year for total precipitation. Above average temperatures along the west coast are expected to continue, and I expect that we will not have any significant relief from those because global warming is a key component of climate change going forward over the next century. And since temperature plays into the Palmer Drought Index, we may anticipate then that the Palmer Drought Index will continue towards drought conditions as evaporation from the surface increases with time without a strong compensating force from increased precipitation. All right, that is all. Any questions?
You mentioned that California has high interannual variability when it comes to precip and weather. Is there some sort of index that measures interannual variability of precip, and how does the high variability in California compare to other places with high variability globally?
I'm not sure, I don't know if any index exists as far as I know. probably one of the reasons why California is so susceptible to this variability is because so much of its moisture comes during a relatively short season. And since the precipitation occurs over that short season, small changes over the short time frame can have serious consequences for total precipitation over the whole year.
Does the PDSI or PMDI and that demand calculus take into account land use changes?
I believe some versions of it do. I'm not sure about the PDSI or the PMDI specifically, but in order to account for evapotranspiration, which is basically evaporation from vegetative surfaces, there is some empirical measure of which correlates land use to total evaporation.
Yeah.
Any other questions? All right.
So Paul did a nice job on the atmospheric science side of things, and we thought it would be nice bookends for me to come in and talk about the hydrology and water resources consequences of the 2012 to 2014 drought. The hydrology is, of course, the science behind what leads to water resources availability. So I think oftentimes people cross these two and think, well, it's all about water, right? And there is this hydrologic response. I'll try and sneak as much of that in as I can. So the objective, at least, is to get at the effects on water resources in California. And as we're looking at surface water and groundwater primarily, since in the rest of this middle part of the course, it's also my job to teach you a little bit about hydrology and water resources. I'm going to take this opportunity to do that with respect to groundwater, since a lot of what's happened in the response to the California drought has to do with groundwater. So I'll start in part of this with some of my groundwater fundamentals and overdraft and negative consequences. What is overdraft and what are the negative consequences? There's several negative consequences that are not being considered openly. And sustainable yield, what is that? And the myth of fossil water, which some of you may have heard about off and on in this context. I would like to say a lot more about ecosystem effects, but a lot of these things are not heavily and directly monitored. I can wave my arms about it, but I don't have a lot of direct evidence yet of ecosystem effects, but I know they're happening. I'll allude to it. Agriculture effects, this has been fairly quantified in an economic sense, in water quantity sense. I'll refer to that. And the economic effects are primarily here in the context of agriculture so far. Types of observations, surface water observations. Here's Lake Oroville, 2011 and to 2014. So this is pretty obvious. Anyone who's driving around California can see this sort of thing. That's the surface water observation. And the two big tanks that we draw water from are the surface water and the groundwater. The kinds of observations that you will be exposed to in groundwater are things like this. And maybe some GRACE satellite data, which I'll show some of, but with some cautionary words on that. This is water level data from a well that's a supply well for City Davis. And the drought period is this latter period, but there are also some concerns of what was going on in this well before the drought period. Near the end of this talk, I'll bring in data from not only the city's wells and the campus wells, so you get a picture right here of sort of what's going on with the drought and the different aquifer systems. These things, they give you, images of parts of the system. Of course, they ignore the snow. Paul showed some nice images of the changes in snowpack, and that's been somewhat quantified. The mountain groundwater, The groundwater beneath the mountains, of course, is not well understood or quantified. But the surface reservoirs are the ones that are really well quantified. We'll take a look at those. The alluvial valley groundwater, I'll look at the evidence of what's gone on there in response to the drought. Okay, here's I think most everyone has seen this. The nice thing about those GRACE satellite images is, they give, I don't really trust them for telling me what's going on in something as local as the Central Valley, but over a much bigger landscape, it's probably, the GRACE images are a good indication of the drawing of the landscape. And here's the GRACE drawing from 2002, 2008 to 2014. One of the problems with GRACE is the size of the footprint, which I think is what makes it hard to take the data and relate it to the Central Valley itself. But again, over the larger landscape, I think it gives a good indication. I would say not all that quantitative, but here's the map that Paul showed, the U.S. Drought Monitor map, and here's an inset of the status of the reservoirs, and we'll just blow that up. It's not a great copy, but these are the major reservoirs in the state, and the historical average reservoir levels for this time of year is shown by the red line, and of course, most of and the blue is percent of capacity, the red is percent of historical average capacity. So most of the reservoirs are 35, 41, 45%, 61% at Folsom Lake, 58, 20. So Pyramid Lake is, they think that's being refilled from probably the Colorado River. That's one story, is that Southern California is a little bit less prone to being negatively affected by this drought, partly because they import water from the Colorado River, which is also under drought, by the way, but California has its water rights. And also, Southern California is more used to living under dry conditions. And actually, they've been very successful in the last 20 years in instituting conservation measures. But overall, the reservoir levels are between 20 and 60% of what they would normally be this time of year. And it's not only the dry conditions, it's the thinner snowpack and the earlier snowmelt that's causing that. Other evidence, and this is a composite from JPL. Whenever it's JPL, that's involving something to do with GRACE. Have you gone over GRACE, Paul, as to what it is? Maybe I assumed that you know what GRACE is. GRACE is a satellite instrument that measures minute changes in the Earth's gravitational field. And those changes in the Earth's gravitational field are then related to, or can be related to, changes in water in the system, on and beneath the surface of the Earth. It is a technique which I think is very interesting and useful on the large scale. On the smaller scale, like looking at what's happening in the Central Valley using GRACE satellite data, I have not seen an adequate error analysis yet. So I don't quite trust it for more local scale information. But what we have here is 1962 to late, or up to the present and beyond, of cumulative groundwater loss in cubic kilometers on the left. On the right is groundwater loss in million acre feet. The red line is from USGS and others' data and models of the Central Valley. This is for Central Valley wide, and it shows the depletion of groundwater over this time period. The green line is as JPL's attempt to take GRACE and key it to more conventional hydrologic data and to continue this trend. The models and data that the USGS has been using are not yet, or not quite ready to be published for the years after the end of the red line, which is about, what, 2004 or 2003. But this is a good indication overall of what's been going on in the Central Valley. The state's Department of Water Resources California Water Plan has indicated pretty consistently that California's in overall overdraft in its water use by about 1.5 million acre feet per year. So this is a million of acre feet per year. If you take a 1.5 change, actually about 1.4, over this time period, you get from about there to there. So this is consistent with DWR's estimate that, that as a state, we're using 1.5 more million acre feet per year than we have. We have it in the groundwater, but then there's this groundwater overdraft issue, which we'll get to. Most of this change, though, is in a particular part of the Central Valley, and it's the Tulare lake bed. Here's an image that is from the USGS also, and from the data and models on the groundwater system. Keep in mind, the Central Valley is divided technically into 4 parts: Sacramento Valley, in green, the Delta and East Side streams. The San Joaquin Basin is the blue. And then this area here, this southern part, is the so-called Tulare Lake Basin. Most of the change you see here is happening down here in the Tulare Basin. And that's predominantly ag pumping. We'll take a little bit more of a look at that here in a little bit. But as you can see, okay, the Tulare Basin is in this purple color. The Central Valley as a whole is the dark blue. But if you go to the other parts of the basin before this drought, the trends were either upward or pretty level. So, and these kinds of disparities in trends in these 2 parts of the system have held also between 2002 and pre-drought, pre-current drought. So most of this then is due to what's happening down here in the Tulare Basin. And that's where we get a lot of the nasty effects that make the news, like subsidence. What is that, and who cares about that? I'll talk about it. There has been a fair amount of response. And by the way, these slides were posted last night, but I've rearranged the order of a couple of them. They're all here, but there's a little bit of shuffling. So if you're working from the slides, you'll notice some of these have been moved around a little bit. If you go to the ACWA website, that's the Association of California Water Agencies. This is the association that consists primarily of agencies that supply drinking water, so big metropolitan drinking water purveyors. There's some ag districts in here, but it's primarily urban, suburban, and big water purveyors. And there obviously, I think anyone who's been around in California for the last 6 months knows there's been a response. For example, you might have heard in the news that Sacramento, its objective, based on the governor's prodding, was to reduce water use by 20%, and the data is in, and they reduced water use in Sacramento County by 19%. They did that primarily through watering restrictions. So urban areas that supply drinking water in Northern California have this elasticity that they can work with, which has to do with the water they use for watering turf. The turf water, we like it, but it's expendable. So the way the drought response has gone in those places, like Sacramento County, has been primarily to water the grass less. And that can result in pretty much instant cuts. It could be cut quite a bit more than it already has been. In Davis, I think 60 to 70% of the water, the drinking water use, is for irrigation, for landscape. In Southern California, it's considerably less in many parts of Southern California. But the red are mandatory restrictions, yellow voluntary measures, the brown or drought emergency, water shortage declared. These are areas, many of them small towns, where people, the water purveyors actually ran out of water. So there are a number of communities that reached emergency situations where water had to be trucked in. And that's, many of those are the brown. Agricultural reductions. Aqua is not a big ag agency, but these ag reductions do not really capture the whole picture of what went on in ag, and I'll get to that in a moment. A good summary of what went on in agriculture is in a report put out by Richard Howitt of UC Davis and a number of other folks from UC Davis that I'm sure you recognize. And this report is available at the Watershed Center website. It was done in July, but it still gives a good, fairly current picture of the drought impact in the context of ag economic analysis. The surface water reduction to agriculture amounted to about 6.6 million acre feet. They estimated, although this is not measured, this is inferred, that the groundwater pumping was increased by about 5.1 million acre feet to compensate for that, with it yielding a net water shortage of 1.5 million acre feet. Basically, what they have done is they look at the crops that are being grown, and they compare that crop water demand to how much the surface water deliveries were reduced, and assume that, well, they must have made up for it through groundwater pumping. It's a no-brainer that groundwater pumping increased a lot, but again, it's not measured directly. And the drillers who drill water wells have been working with all their drill rigs and all their crews like day and night through the summer to drill more wells, to deepen more wells, because as water levels go down, more shallow wells dry out and have to be deepened. The crop revenue loss, $810 million. The additional cost due to pumping groundwater, because it costs more money to pump groundwater than to get surface water, $454 million. Livestock and dairy revenue loss, $203 million. So total direct loss is $1.5 billion. Total economic cost, $2.2 billion. Job losses, primarily in the Central Valley and southern part of the Central Valley, 17,100 job losses. So these are important impacts. In the context of the overall California economy, what's the scale of the California economy in terms of gross domestic product? It's about $2 trillion per year. So these numbers are small relative to the total California economy. That's why one of their conclusions is, in terms of the overall economic hit for the state will absorb it, and has. In terms of the economic impact to localities like the Central Valley and many of the small towns in it, it's much more significant. Something that's not addressed here is the impact on the food supply. Okay? California supplies a lot of food, like half approximately the fruits, nuts, and vegetables for the U.S. I've not yet seen an analysis of the effects of the drought on the food supply. Has the rest of the market absorbed the additional demand stemming from California cutbacks and land fallowing? I would presume so, but I haven't seen the analysis. Two key conclusions that came from Richard Howitt's report, that this drought, the 2014 drought, which is really, I look at it as the third year in 3 relatively dry years or drought years. It's the greatest absolute reduction in water availability for California ever seen. Okay. And surface water availability reduced by about a third. And then the next one, groundwater availability and use is the key to agricultural prosperity in the 2014 drought and future droughts. So this year, groundwater may replace as much as 75% of the roughly 6.6 million acre-feet loss of available surface water. And then the bottom line here, failure to replenish groundwater in wet years will continue to reduce groundwater availability to sustain ag, particularly more profitable permanent crops during California's frequent droughts. So it becomes, this issue of groundwater. And earlier in the class, I had this bank account analogy. It's the perfect illustration of this problem where you've got all your water in the 2 bank accounts. The surface water is relatively well known. Then the rest of your water is in the groundwater. It's not well monitored or known, but they are connected. So that's where we are. Now, we have dipped into the groundwater in a big way and in an unprecedented way, and now we're trying to figure out what to do. It's led to legislation. So at the end of this set of slides, there's a brief slide that just summarizes the groundwater legislation, which would not have been passed, most likely, without this drought. So I suppose you could say in this case, this is a disaster that was not wasted. Okay, so I forget why that's there, so I'm going to skip it and come back to it. Okay, oh yeah. So, one of the things that has gone on with all the groundwater production in the southern Central Valley is subsidence. And let's look at some of the subsidence data and then circle back and talk about how that works. Here we have a groundwater hydrograph, which is nothing more than a graph of groundwater levels through time. And so here's, this is the Tulare, this is southern San Joaquin Valley, or the Tulare Lake Basin. And you see the groundwater levels that started at 90 feet above sea level, and today they're on the order of 150 to 160 feet below sea level. On the right-hand side is vertical displacement. And this is from a continuous GPS monitored site. And it shows that the land is displaced from about 0.05 down to, so that's 0. So basically about 0.2, 2/10 of a foot vertical displacement. There's a ranch in Yolo County called the Conaway Ranch, which is on the Yolo bypass area between 80 and 5. Okay? That ranch has been pumping a lot of groundwater and selling it. They've experienced a full foot, more than a foot of subsidence just during the last year. So this is an unfolding story. It's an old story because in the past, groundwater has subsided a lot, which was one of the motivators for creating the state water project and some of the other projects. But here's an example of what has gone on, and you see as the drop in groundwater levels accelerates, the subsidence accelerates. And again, in this case, subsidence is just as it implies, it's a subsidence of the land surface. It's due to compaction of the non-aquifer parts of the system. Again, I'll come back to that. As I said, it's not new. Here's a map of the subsidence between 1926 and 1970 for the San Joaquin and Tulare Lake Basin parts of the system. And here, this is subsidence in feet. And there are some areas where during that time period the subsidence was as much as 24 feet. And we'll look at the telephone pole photograph that most of you have probably seen. This happened before there was much surface water delivery to these areas, primarily for agriculture. And people knew that it was happening in the 20s, 30s, 40s, and 50s. Without this happening, the state water project probably would not have been built. That project was built in part to replenish the farms that were overproducing the groundwater and causing subsidence in this system. What's happening now is history repeating itself. The surface water deliveries have been cut, so the farmers are pumping more groundwater. This is not a very good image, but again, this is from the recent state water plan, the California Water Plan 2013, Water Plan Update. This is the Tulare Lake Basin area. The report for the Tulare Lake Basin is out in draft form, so you can see some of the information. This is spring 2005 to 2010 change in groundwater elevation. So this is before the drought. The drought has just kind of accelerated what was already going on in this part of the world. And you have a drop in groundwater levels here of, gosh, that's really hard to read, isn't it? That's about, the maximum right there is about 65. This is 53, I believe. That's 40, just recalling in part from memory, 49 or so, minus 20. So these are big drops over just a 5-year time period in water levels, groundwater levels in this system. The more the groundwater levels drop in this kind of situation, the more subsidence occurs and the more other overdraft consequences occur. Subsidence is not the worst of it. There's another long-term insidious effect of groundwater overdraft on the long-term water quality. And I'll give a little bit of a sketch on that in a moment. That's what I should have done, is blown it up. I forgot I had this blow up in here. So these are big drops in water levels. In fact, in that system, in this this part of the Central Valley, it's ranked, I think, in about the top 10 most overdrafted groundwater regions in the world. And I wasn't able to verify this last night, but I heard a statistic that the pumping of groundwater in California accounts for more than half the total groundwater pumping in the entire U.S. It's a very productive groundwater system, so people have been tempted to overproduce it, and that's one of the things that's happening. So I've alluded enough to some of these groundwater processes. Let's very quickly go into some of the fundamentals of groundwater. Yes?
I'm just wondering if it's possible to reverse that trend of vertical displacement if you recharge groundwater at all. Like, can the land go back up at all?
You can go back up a tiny amount, but this kind of subsidence is what is known as inelastic subsidence. It's not recoverable. Right here, we've probably dropped a meter in the last half century. And maybe we're dropping faster now, as you'll see when I show you what's going on in Davis, which was an eye-opener for me. So, and you're sitting right on top of it, so I figured you ought to know what's going on. So groundwater occurrence in California in the west, it occurs in these alluvial valleys. These are basins filled with alluvial sediments deposited by rivers. So the big ones, the Central Valley, you've got the Salinas Valley, the coastal basins. And the basin and range are these light blue regions here, for example, throughout Nevada. Then you have volcanics up on the Modoc Plateau in California. Southern California, part of the Mojave area, is also basin and range. Again, so wherever you see blue here, it's alluvial material. These are the most productive groundwater aquifer systems. There's groundwater everywhere too, up in the mountains, but the rocks in the mountains don't release that water as readily for production. So you can go to the National Atlas and pull up maps like this on where the major aquifers are throughout the country. Where does the water reside in these systems? Inside the pores or cracks in the rock. the water that the groundwater we're standing on top of in this part of the valley is in the interstices between sand, silt, and clay grains. So these are unconsolidated sedimentary rocks. There are, in the mountains, the water sits in cracks in the hard rock. There are cave systems known as karst, where the water is in caves. Lava flows can lead to lava tubes, as you see in this picture, and extensive fracturing, which can move a substantial amount of water. What is groundwater? Anyone who's been to the beach and dug a hole in the sand and the beach has dug into groundwater, right? So when you dig the hole at the ocean through the sand, you're hitting the water table, right? You dig the hole and the water stays in the hole. Just to define some things, if we take a slice through the earth vertically, the water table is this surface right here below which the pores in the rock, that is these pores, are fully saturated with water. Okay? In reality, it's not flat like this. It's much more dynamic. So there's more cartoons later. Then we have above the water table what we call the unsaturated zone, where there's water, but there's also air in the material. The soil zone, incidentally, these materials that look like that are not soils. Soil is something much more special. The soil is typically the upper meter or two. It's a much more biologically active part of the system in terms of microbial life and plant life. Geochemically, it's different. The texture is different. But that's what we call the soil zone. The rest of these materials in the Central Valley here are called sediments, geologic sediments. So the groundwater is technically everything below the water table. Then there's this zone called the capillary fringe where there's, if you will, a little bit of wicking of water. There's a capillary rise to the water where this zone is almost fully saturated. And it can be anywhere from millimeters thick to tens of centimeters or maybe even a meter thick. So unsaturated zone, saturated zone, which is the groundwater, and water table. Here's another image of the water table in more of a natural environment. The water table is this dashed line. It's inclined, typically, and often connected to surface water. In a system like this, the water's moving. Beneath our feet right here, the water's constantly moving. It's not a big tank of water that just sits there, that we pump water out of and water gets in somehow. It's a very dynamic system. And if there's a perennial surface water body like this one, the reason it's perennial is it's being fed by groundwater. The materials that make up these aquifer systems, and sorry about the font here, but this looks like, oh, it's just a big pile of sand. Our aquifers here in the Central Valley do consist of sand and gravel, but most of the subsurface here, if you drill a well right here, most of what you will encounter are clays and silts, which do not release water readily to wells. And what are these materials? Basically, gravel are coarse materials that are on the order of inches or fraction of inches. Sand size much smaller, and here are the sizes in inches given here on the scale. Silt size is a particle that's barely visible to the eye. So it's a tiny, tiny particle. And then clay, the particles of clay are invisible to the naked eye. So the materials that make up the aquifer systems are gravel, sand, silt, and clay. And the aquifer parts of them here are mainly sand. Right here beneath Davis, the percentage of the system that consists of aquifer materials, sand or gravel, is only about 20%. 20%. The rest are these silts and clays. Okay? So these store water, but they don't release it to wells quickly. But they do store it. It's a very important function. And here's an example of what gravel looks like. I think everyone has an idea of gravel, sand, and clay. potter's clay is a perfectly legitimate example of what a clay is like. These clays, obviously if you pour water on the gravel or the sand, what do you expect to happen? The water is going to move readily. So we refer to that as permeability. These materials are relatively permeable. Clay is much less permeable, hence it does not release water readily to wells. More on the dynamics of water and groundwater and how it occurs. Here's an example of a basin. You've got water coming in. The water table is inclined. The water moves pretty much in the direction of the water table. I'll circle back later and give a little bit more technical explanation of some of these things, time permitting. In this case, there's what we call an unconfined aquifer above, and then there's a clay layer, low conductivity confining unit, and a confined aquifer. Most of the water that we take out of the Central Valley comes from these confined aquifers. Okay? And the way the storage changes in these aquifers, whether it's unconfined or confined, is very different. So the California water problem, a lot of it's about storage and how the water in storage is changing. In an unconfined aquifer, it's simple. The water table, which is this surface here, goes up and down, and it's like water in a potted plant. You fill up that potted plant with water, water drains out of the bottom, the water table in your potted plant goes up and down. The water in these confined aquifers, the storage changes are a little bit more complex and not intuitive. It's not like a big bucket filled with sand. I'll come back to that in a moment. So unconfined and confined. The confined aquifers are overlain by these confining beds. Water gets in and out through holes in these and by leaking through and back out. This figure also shows nicely the groundwater circulation to a stream. Stream base flow represents the flow in the stream when it's not raining or there's no snow melt. For example, right now, the Sacramento River has water in it. The Sacramento River has had water in it all year, even though, for all intents and purposes, in Northern California, it has not rained and most of the snow is gone. So where's the water in the Sacramento River come from? It's base flow originating from groundwater discharge to the stream. So most base flow consists of groundwater discharge to these streams. Here's another image of a confined aquifer on a regional scale. And if we look at the potential energy in this aquifer, and how will we do that? We do it by drilling wells. If I drill a well here and screen it in this aquifer, the water level will be above the confining bed or above the top of the aquifer. And it could even be above land surface. I realize I'm going quickly through this, but I want to get to a point on storage in these confined aquifers. The point here is that the water levels, if you drill wells anywhere along this confined aquifer, are going to be above the top of the aquifer. And when we pump the well, when we pump this well, these potential energy heights or water levels in wells go down, but the aquifer stays full of water. The aquifer stays full of water. So this is a little riddle. We pump water from these aquifers, like these confined aquifers, like in the Central Valley. They stay full of water, completely full of water, but we're getting water out of them. How could that work? In the unconfined system, it's simple. It's like water in your sandbox. Build a sandbox, fill it with water. There's going to be a water table there. The water table goes up and down. That tells you how much water is there. In these confined aquifers, when you pump them and you get water out, and we pump, around here, thousands of gallons per minute per well. It's a lot of pumpage. We pump water out, but it stays full of water. How could that happen? Any ideas? Where's the water coming from?
Well, we're tapping into an unconfined aquifer, probably,
Well,
that is now draining
You
in,
could-
actually through the well itself in some cases.
in this case,
To get vertical conductivity.
that's a good thought. This well is screened just in this aquifer, in this. But yes, you do get leakage, but you don't have to in order to get water out of this aquifer. The recharge could all be up here and moving down like that. Think of a water balloon. You know, you can puncture a water balloon, and it stays full of water, but it deflates. Okay? That's what happens in these confined aquifers. The water is released from them by minute amounts of compaction. When the city of Davis and the campus pumps its wells and remove water from our confined aquifers, you can't see it, but sensitive instruments could measure it. The land surface deflects by millimeters or fractions of a millimeter. That's the aquifer compacting. When we stop pumping here, the aquifer fully decompacts. That's elastic storage. But it also means that in these aquifers, they're under pressure, right? I can drill wells anywhere along here, and because the water comes into the system at a high elevation up here, those high pressures can be maintained for great distances. But when we pump from them, there's a pressure response that spreads very rapidly and far through these systems. So it makes it more difficult to figure out what is going on in these aquifers. How much water is there? How much water have we removed from the storage in the system? That's one reason that, especially since we don't measure pumping rates in agricultural systems, that it's hard for us to know what's going on in the groundwater system. Knowing that the changes in storage in the system requires models that relate these pressure changes to the geology and the storage changes in the aquifer itself. We have the models. Some of them are not quite good enough yet to do this properly. One thing I'd like to point out here, in a system like this, this could be tens of kilometers in extent. Very commonly in a regional groundwater system like this, the time it takes the water to get from the recharge area to this well could be thousands of years. Thousands of years. So you're hearing in the press and in a lot of outlets and talk by water resources experts that if you're pumping groundwater that's thousands of years old, that's fossil water. That's fossil water, which means that connotation of fossil water is once you take it out, it will not be replenished. And that's false. That's the statement I added here. That's a myth, that old water that's thousands of years old is fossil water that is not replenished enough to support pumping. The water you're drinking here is thousands of years old. But as I'll show you in a moment, the groundwater levels in Davis until recently have not been in overdraft. Even though we've been drinking for 60, 70, 80 years water that's thousands of years old, it's replenished. So how could that be? How could water that's thousands of years old and that we're taking out of the ground and drinking be replenished? The rationale that people are using, and again this is wrong, is that water was in place during the Pleistocene or something like that, and it's not going to be replaced. Again, it's wrong. And why is it wrong? Well, these systems are big. These groundwater systems are bigger than the Great Lakes, many of them. They're like small oceans underground. They're fragile. So it can take thousands of years for water to get from there to there. And we may take the water out at this well that's thousands of years old, but meanwhile the water's still coming in to the system. The other analogy to think of is the oceans. The mean residence time of water in the oceans is 3,000 years. We don't say, oh, if we remove the water, some of that water from the oceans, it will never be replaced. Why don't we think that way? Well, because we know the ocean is a vast storage container of water. And the reason it takes thousands of years for the water to cycle in and out of the oceans is because they're so big. It's the same way in many groundwater systems. Where there's fossil water, it does not mean the water is not developable or not going to be replenished if we pump it. There are cases, and I think we may be seeing this now in the Davis Deep Aquifer, where we are exceeding the capacity of that system to support the pumping both by the city and the campus. And I mentioned here that sometimes the water levels can be above land surface. That's why we get flowing wells. Here's a picture of a flowing well. It's somewhere in the southern San Joaquin Valley. I don't know where, but there used to be many of them. We would drill wells and the water would flow to the surface. That's a case like this where it's a confined aquifer. The well punctures the confining layer and the well flows to the surface. Groundwater and surface water are interrelated. They're integrally related and inseparable, really. Here's a nice image of how a groundwater system transitions from water flowing from upland areas to a stream, generating base flow. And what happens when we develop groundwater by putting in wells between the stream and the recharge area? We create a cone of depression, which depresses the water table. In this case, we draw water into the well. And if we keep pumping long enough, we can start drawing water out of the stream. So in the Central Valley, most of the groundwater has been sufficiently depleted that we have depleted water out of the streams. Basically, every stream in the Central Valley now has depleted or almost no groundwater base flow because of groundwater development. There would not be water in most of the Central Valley streams in summer if we didn't have reservoir releases upstream, storing water and releasing it into the system. And this depletion of stream flow has had an effect on water that's available for the ecosystem, including fish, and the migration of Chinook salmon, for example, along the Cosumnes River has been impaired due to groundwater pumping, which has reduced stream flow, which makes salmon migration at this time of year difficult because there's no groundwater discharge into the stream to support the low flow, stream flow that the fall run of the Chinook salmon need to migrate. And obviously, if we start to dry up the stream, we're going to affect wetlands near the stream. The Central Valley used to consist of about 20% wetlands and riparian forest, which has been compromised by groundwater pumping. So here's a good image from Claudia Font's publication in the USGS on the Central Valley Groundwater Water Model, CVHM. And it's a picture of the San Joaquin Valley pre-development and post-development, just to give you an idea of what has gone on. We've got a stream here, San Joaquin River. Before development, the groundwater was moving through the system and discharging to the stream. And there's a major confining layer right here called the Corcoran clay. Essentially, the whole system is confined because, although it's not shown here, there's so much clay in it that basically wherever you drill a well, it's a confined condition. Water comes in from the mountains, and much of that infiltrates at the heads of these alluvial fans and forms recharge areas that you see near the mountain fronts here. But overall, it's a circulating system. Water comes in, water gets out. Here's a post-development situation where pumping by wells has lowered the water levels to the point where the river is now recharging the groundwater system. We're applying irrigation water from the pumping of the wells and from imported surface water, and that's adding recharge to the system. Notice at the bottom of the system, they've got saline water. Actually, there's a lot more of it than that. Basically, in these groundwater systems right here, we could drill 1,500 feet and encounter fresh water. Below about 1,500 feet, we encounter salty water. And not just a little bit. We could drill thousands of feet more and keep encountering salty water. All these groundwater basins are surrounded at depth by salty water. It's not ancient seawater. It's just groundwater that is circulated so slowly that it's dissolved enough of the rocks that it's become salty or brackish, in some cases almost as salty as seawater. A concern here is if we overproduce the groundwater, this is one hazard of groundwater overdraft. If the water table keeps dropping in a system like this, we can start to pull in the salt water from depth. And that has happened. So if you overproduce the fresh water in a groundwater system, you can essentially pull in the salt water and, for all intents and purposes, permanently degrade the water quality of the system. This is a danger of groundwater overproduction that has not been mentioned. Another concern here is that when we do this and we cut off the natural discharge of the groundwater to the rivers, we create a closed system, right? So in this case, how does water get out of this system? These arrows represent irrigation water. What's the main exit for the water? It's the wells. So we've created a closed system. Water gets in by irrigation primarily, and some inflow from the streams and by imported surface water. Water's getting out not by stream flow and flow out to the ocean or to a sink, but the water's getting out by evaporation from the crops. So we've created a closed system. So that this is another concern of groundwater overdraft. We cut off the natural discharge of water to the system. We're basically capturing all the inflowing water by wells, but reapplying that water for irrigation. The irrigation water evaporates, evapotranspires, leaving behind the salts. So we're concerned that this sets up a recipe for salinization of not just the soil, but of the entire groundwater system. The time scale of this salinization would be a century or more. The models to compute that are still being built. Here's an image also from Claudia's USGS publication on vegetation types in the Central Valley before groundwater development. And you have a lot of floodplain habitat in green, riparian habitat in blue, valley foothill hardwood, these riparian zones along each river, and lots of aquatic and in royal blue and light blue and wetland areas. Those were all, basically everything you see here that is a vegetation type was fed by groundwater. Surface water, of course, was important, but without the groundwater, none of this would be here, and with groundwater level reductions that have occurred in the Central Valley, most of what you see is indeed gone. So this has been a major ecological effect of groundwater development in the Central Valley, that most of the wetlands and riparian zones that used to be in the system are now gone because of groundwater production. Okay, there's a picture of a well being drilled. What is a well? A groundwater well is basically a tube in the ground with a screen that's used to strain out the materials that make up the aquifer system. These wells consist of perforated pipe or screens to keep the sand, silt, and clay out of the system. There's an example of what a well screen can look like. The water in many of these systems is pumped by turbine pumps. When you see out in the field a pump that looks like that, or this thing sticking up out of the ground, that's a well with a turbine pump, which is a motor that turns a shaft at depth that pumps the water up to the system. These things were invented and made available in large scale not until the 1940s and 50s. So by the 40s and 50s, we had the capacity to pump a lot of water. So that's when this pumping boom started. So groundwater overdraft. Let's define it. It's pumping more groundwater than the system can sustain. But the thing is, the sustainable thing is subjective. It's subjective. So what are the consequences that we use to define sustainability in groundwater? Basically, overdraft is pumping more than the system can sustain, and we declare the system non-sustainable when bad things happen. Well, what are the bad things? The bad things are land subsidence, water quality degradation through saltwater intrusion or the kind of upconing of salty water that I mentioned, ecological degradation that I've been mentioning, and increased energy consumption because the pumping lift is greater. It takes more energy to pump the water, and if we go in that non-sustainable state for too long, we can run out of water. Okay. The subsidence, the case example of subsidence that most of you have seen is the photo of Joe Poland of the USGS shot in 1977 showing the land surface then and what it was in the Mendota area of the San Joaquin Valley back in 1925. So this was a hot spot for land subsidence. It does not ruin the aquifers. It compacts the clays and silts primarily. So people say this is going to ruin the aquifer. Well, that's not true. But it can reduce the storage of water in the non-aquifer parts of the system. And it creates disruptions. It's affected the State Water Project by making the canal of the State Water Project such that it's in certain sections has been flowing back upstream because of subsidence. So they're having to re-engineer parts of these canals to get water to continue flowing in them. It can offset railroad tracks like an earthquake would. It can offset foundations. It can affect roads. And so it's a problem. It's not always the worst thing in the world, but it is rather undesirable. The levees on the Yola bypass have subsided. Those are flood control levees. So naturally, we could be at greater flood risk because of subsidence of the levees that protect us from floods. There can be cracks. These are subsidence cracks in Arizona from groundwater pumping subsidence. In Florida, they get a lot of this happening where they dewater their limestone formations and they get cave-ins, sinkholes caving in. Here's a bigger one, also west central Florida. Seawater intrusion is where overpumping brings in seawater in the groundwater system that's at the coastal interface. Very similar to what can happen right here. If I overproduce groundwater, I can bring in essentially salty water from depth in the system. This issue of groundwater becoming a closed basin and we're just recycling the water within that basin, the Tulare Lake Basin is a prime place for that. This shows the groundwater elevation contours and the flow directions in that system. Basically, none of the water is getting out into the rest of the Central Valley. Essentially, it's all staying internal here. So we're concerned that the life of potable water in that entire system is in jeopardy, not just because of groundwater contamination from fertilizers and so forth, but from the overdrafting of the system. So the danger of a hydrologic basin losing its outlet and cutting off the removal of salts. We've already gone over this. So let's quickly now look at Davis. These plots are available online. This link is live. Elizabeth Case with the Davis Enterprise worked with me or asked for help from me on interpreting the Davis data. I hadn't looked at it in a number of years, but the city of Davis and the campus pump from a system that has three, not very distinct, but three functional parts that are referred to as shallow, intermediate, and deep. The deep aquifer is approximately greater than about 1,000 feet deep. The intermediate is greater than about 400 feet. So shallow, intermediate, and deep. The city historically is pumped mainly from the intermediate so-called aquifer system. And you see what's gone on. Before the drought, water levels will go down 70 feet and recover entirely the next year down. This is that pressure response in the confined aquifer. Huge changes. People just started looking at some of these this summer and they said, oh my God, the water levels went down 50 feet last month. Well, they always did, but they always recovered. But you can see what's happened now with the drought. The recharge is less rainfall, more pumpage, drier conditions, more water demand, and that is taking a toll on the system. So there's the drought effect here. It's not a big effect. It's not like the Tulare Lake Basin effect, but it is happening. Okay, here's the deep aquifer, and in the report in the PowerPoint that I uploaded to the site, this was mislabeled as intermediate. But this is what's happening in the deep aquifer. It has been happening for some time now, apparently, but no one's been minding the store, as far as I can see. Here's the deep aquifer water levels, and yeah, you see an apparent effect of the drought, but there are also trends happening, and it's not just this well, there's multiple wells. The deep aquifer is being now produced out of by not only by the city, but and the campus. The campus, our drinking water here has always come from the deep aquifer because it's better water. It's less hard. Has less calcium, magnesium. The campus has another set of wells in the intermediate aquifer that it uses for its utility water, landscape irrigation, lab water, and probably cooling water for air conditioning. But what I think has happened is because the city has moved more into the deep aquifer because their intermediate depth wells have been contaminated with nitrate more and more, that the campus and the city's wells are now interfering with each other. And these are big drawdowns. This is below sea level. So some of these wells, the water levels in them are 1,000 feet below sea level. That is a problem. It is also why it's probably a very good thing that the city of Davis and Woodland have voted within the last 18 months to import Sacramento River water. So this is a classic case of overdraft, maybe not in the whole system, but in that deep aquifer. Here's the campus's wells. The drinking water wells for the campus right here are all from the deep aquifer. They're all deep wells. And lo and behold, those have been going down for about 10 years. We don't really see an effect of the drought. We see an effect of a little bit of laissez-faire management here, or an effect of the city of Davis pumping more and more water out of the deep aquifer. As far as I can tell, below the early 2000s, the water levels in the campus wells, they were up and down, but there was not a discernible trend. When Davis, the city, started drilling more wells in the deep aquifer, we have this going on. And here's one of the campus's intermediate depth wells. And yeah, maybe the last 3 years, an effect of the drought there, not a big effect, but it's in the order of 5 or 10 feet. But overall, it has its ups and downs, but not a strong trend. This is kind of typical. So this is kind of similar to what the city sees in its intermediate well. So we're seeing an effect of the drought in the shallower groundwater. We're seeing an effect of groundwater management issues in the deep aquifers here that the city and the campus need to address. And in fact, when the city started to drill more wells in the deep aquifer 10 years ago, they started to talk with each other and say, hey, we're not sure you can do that, City of Davis, because the campus is already using that water, And we don't know how much that aquifer can sustain. I think now we're seeing how much the deep aquifer can sustain. I'm out of time, so I'm going to skip over this and just summarize the new California groundwater legislation. This is a very cursory summary. But basically, the three things it does is provide authority to a groundwater sustainability agency to impose certain fees for management of groundwater. It authorizes these agencies to adopt and implement a groundwater management plan. Now, this sounds like common sense, right? But in California, prior to this has not been the case. And there are deadlines on it. Basins have to be prioritized by January 2015. That is, which are the basins that are most in overdraft? So you'll have basins looking at water level hydrographs like what I was just showing you, trying to decide, are we in overdraft or not? Before I started looking at the data this summer, which I hadn't looked at in a long time, I thought, we're okay here in Yolo County. Now I'm not so sure. Then there's a deadline for report on basin conditions, best management practices, and a monitoring program in the 2016-17 time range, and then determination of successful management or not with probationary action. That is, have you implemented your management plan and have you corrected any problems? And if you haven't, there's going to be action taken against you, and the time frame for that is 2020, 2025. So these are revolutionary for California. And again, this is probably the biggest consequence of the drought. The rest of the stuff that's going on in the groundwater, well, a lot of that was happening before the drought. The drought exacerbates it. And then there's the issue, this is from Paul's slides. What if this is a longer term drought? And we don't know, right? But it really begs the question of, what do we do if this is the beginning of a much longer dry period, and that we've been in such a relatively wet period that we've designed our entire water infrastructure to in the past 50 years. I will leave it at that because I'm 10 minutes over. So I think we can take some more questions. And the camera still has tape. Yes?
When you were talking about overdraft being defined as pumping more water than the system can sustain,
Right.
By sustain, do you just mean replenish, or is that a more vague definition?
It's vague.
Okay.
So sustain means, well, anytime you pump a groundwater system, you're going to be taking water from somewhere. You're going to be reducing stream base flow or wetland to some extent. It's a question of whether it's a change that's perceptible or significant. And if it is a significant change, is society willing to live with it? So you might say, by groundwater development in the Central Valley, we eliminated most of the natural wetlands. It wasn't agricultural drainage that did this. It's the groundwater pumping. Society may say, well, we're not willing to live with that. So you could say, by that rationale, you could declare that as of 1970 or 1960, most of California or Central Valley area was an overdraft or non-sustainable. But we don't define it that. We haven't. Most of those drying up of wetlands happened, people didn't connect the cause and effect, and maybe they didn't care about the wetlands as much when they were drying out. So it happened, and we live with it. But now it's more, okay, do groundwater levels keep going down, which is obviously non-sustainable. Eventually you could empty the water out of the container. Power prices go up as the groundwater levels go down. You can continue to reduce stream flow by doing that, which could further exacerbate ecosystem recovery. So again, it's a subjective definition.
Yeah, so related to that threshold acceptability, I think certain regime shifts that we might see, the points at which the system changes in kind of fundamental, fast ways. And do you see any kind of hydrologic regime shifts that have occurred or can occur that might change the direction of these trends or tendencies very, very quickly?
Well, you know, where the water levels keep going down, it's just clearly a case of non-sustainable pumping. The water is not being replenished. So in terms of these, like we hit a threshold condition, most of that here happened 50 years ago. When, you know, you would have been, and you can see it in some places today, like in Scott Valley, where groundwater, pumping has been shown to have caused reductions in stream flow recently. So we can measure it. But most of the effects in the Central Valley, like the Tulare Lake drying up, a lot of the streams losing their base flow, a lot of the riparian forests along the streams going away, the wetlands, the bottom, the Tule marshes and the wetlands along the San Joaquin and Sacramento River, most of those transitions happened at a time when people weren't paying attention. So those would have been pretty clear threshold switches of the system.
But these systems don't operate with kind of two steady states, two regimes. And as I understand it, there might be something else. We might drop into yet another regime entirely.
Well, in this case, the other regime would be we're upsetting the balance of freshwater input and output enough that we start to affect the water quality.
Yeah, and that's kind of a long-term.
That's a much more insidious, creeping normalcy kind of problem.
With all sorts of implications.
Yeah, if we salinate the large part of the Central Valley, I don't think we'll be irrigating in that area at all. Are we going to desalinate our irrigation water?
And our hopes for ecosystem restoration also compromised.
Well, if most of the land went fallow because the water became unusable and the soil's saline, over a period of decades or centuries, the fresh water would eventually start to replace the salty water in the system. But it would be a long, for our generation and our kids and perhaps grandkids' generations, you'd be writing off that part of the world.
Yeah.
Other questions? So that's the picture of the drought from the perspective of a groundwater person.